Hi everyone. So far in this course on analog electronics, we discussed a wide range of circuits. We saw circuits which can perform mathematical operations like addition, multiplication, division, subtraction, integration and differentiation operations. Then we also saw a class of circuits which can perform clean amplification of differential input signals. And such circuits also had great CMRR. And we performed a detailed mathematical analysis of all these circuits. We saw their frequency response, and we also talked about uh, the transient response of those circuits. Now I felt we should discuss another class of these analog circuits, and I shouldn't call them purely analog circuits, rather I'm going to call them as mixed signal circuits called comparators. At its heart, a comparator as shown here is a simple three-terminal device. It's a very high gain amplifier that always operates in open loop. So let V1 and V2 here denote the input non-inverting and inverting input terminal voltages, and V0 denote the output voltage. Then if your V1 is greater than V2, the output voltage will be at plus Vsat. If V1 is less than V2, the output voltage will be at minus Vsat. So if you see, a comparator is a high gain amplifier. It is used in open loop, and therefore it can only produce two output levels. Either it is plus Vsat or it is minus Vsat. The input levels are analog in nature. They can be analog in nature, okay, which means they can take a wide range of values. But the output levels of a comparator are binary in nature. They can either be plus Vsat or minus Vsat. It's like a logic high or logic low level. Therefore, it's not surprising that comparators are often circuits that are found between the interface of the analog and the digital worlds. Okay, and comparators can often drive the output of a comparator because it's a binary output signal, right? It takes only two voltage levels. They can be used to drive digital circuits directly. Now, provided you ensure that there is voltage level compatibility. So what do I mean by that? The logic high and logic low levels of this inverter, of this digital circuit, should match the logic high and logic low levels of the comparator. We'll talk about this later when we talk about the available integrated circuit chips in the market and their voltage levels. I'll talk about it at that time. But because comparator can take only two output levels, they can directly drive digital circuits. So that's the point I'm trying to make here. Now, applications of comparators. Where do you find these comparators? Comparators are widely used in analog to digital converter chips, in analog to digital converter circuits, right? ADCs by definition are the interface between the analog and the digital world. Therefore, it's not surprising that you should find comparators in as building blocks of these ADCs. Other than that, you will also find comparators in mixed signal circuits like pulse width modulation circuits. Right now, let's not, if you're not aware of what PWM circuits are, it's entirely fine. We'll talk about that at a later stage. And you'll also find them in 555 timer ICs. 555 timer is also a mixed signal and mixed signal chip. It's one of the best selling chips out there. And you'll also find these comparators in this 555 timer ICs. Other application of comparators are comparator circuits with hysteresis involved in them, and those circuits are called Schmitt triggers, which we will be talking about in the upcoming lectures. So to give you an idea of difference between a comparator and a regular op-amp, I thought I'll just take a very simple example. Now this part might look very trivial, but I'm just, for the sake of continuity in the lecture, I'm talking about this. So I just said a comparator is a very high gain amplifier. Okay, then you might ask, how is it different from an op-amp? An op-amp is also a very high gain amplifier, right? An op-amp is also a three-terminal device. At its heart, it's just a three-terminal device with a characteristic similar to this, what I've drawn here. It's similar to this. The difference is that a comparator is always used in open loop, and an op-amp is mostly used in negative feedback. Okay, and that is why you see op-amps and comparators as different chips, as different flavors of chips that are supplied by companies. If you look at TI and other companies, they sell you op-amp chips separately and comparator chips separately. In a few moments, we will see what is the difference between the construction of these two integrated circuits. But right now, I'm just letting you know that you have to keep in mind that comparators are sold as separate chips. LM393 is a comparator chip. LM393 series is a comparator chip series, and LM741 is our op-amp chips, okay, op-amp integrated circuits. So just to, for the sake of continuity, assume that I'm feeding an analog input voltage signal, which is a ramp signal shown here, which oscillates between minus V peak and plus V peak to a comparator, and the other inverting terminal of the input terminal of the comparator is fed to a fixed voltage reference Vref. On the right hand side is shown is a circuit which is a non-inverting amplifier built using op-amp, the 741 op-amp, and here the input signal is again fed at the non-inverting input terminal, and you are supposed to find what is the output voltage. So for a comparator, every time your input signal crosses the voltage level Vref in the positive direction, which is when your input signal becomes greater than the reference voltage, the output goes to plus Vsat. And every time your input signal goes lower than the reference voltage level, then the output signal goes to minus Vsat. This is for a comparator. So a comparator produces a binary output. The frequency of this signal is same as the input frequency, but the output, if you see, has only two levels. So you can see it like a triangular wave to square wave converter. I've fed a triangular wave as an input to the comparator, and out came a square wave with two levels, oscillating between two levels of minus Vsat and plus Vsat. If you see an op-amp based circuit, which is built using the 741 op-amp, a feedback op-amp based circuit built using the 741 IC, that produces a same replica of the input signal multiplied by some gain factor. Since it's a non-inverting amplifier, the gain of this non-inverting amplifier is 1 plus R2 by R1. Right? The output frequency is same as the input frequency, and the output voltage levels are a scaled version of the input. If the output was input was oscillating between minus V peak and plus V peak, the output is now oscillating between minus A times V peak and plus A times V peak. Okay, so it is acting like a perfect amplifier, whereas here it is acting like a circuit which produces two output levels that oscillates between plus Vsat and minus Vsat. Okay, so that's the comparator. In the next lecture, we will look at the difference between the 393 ICs and the 741 ICs. Okay, both are amplifiers. What exactly is the difference between these two? Okay, thank you.